So this is part 2 of my video on the Roblox Pipe Dream animations. If you want to know how all the math is derived, go watch the previous video, but in this one we're going to be looking at how the code is implemented. Well, let's just get right to it. Now, one thing to know about this video is that we assume we already have the MIDI note data beforehand. I won't go over that here, how we actually get those. That would be its own video that I might do. Anyway, now that we have all the math laid out, we want to know how we actually put it into practice, and this was one of the first problems that I had to tackle, and I love the solution that I came up with. To start, our math only tells us what values the instruments should take on for just one animation at a time. What if we wanted to have multiple? For example, these bongos move after being hit by every marble. If we were to graph their movement over time, it would look like this, the decaying wave function. Its displacement is 0 everywhere except for after it's hit, and if we set the bongo's position to exactly this value every frame, then it would work, but just for one. We would have a problem if we tried to use multiple at the same time. That being, if we had two animations overlapping, the unwanted 0 value from the first one would overwrite the second. The solution? Instead of setting the values of the animation directly, we add them. And you can see this visually with the graphs, we're adding the effects over time. The problem that then arises is what would you be adding these values onto? In other words, what would happen if you don't add anything? The solution is to keep track of the instrument's default state and then reset to that at the start of every frame. This way, the instrument's position is defined for any number of overlapping animations. With just one, it functions identically to if we were setting the value every frame like we did earlier. With two or more, then applying every animation just adds the effect onto the previous one. And because it resets every frame, we don't have to worry about parts slowly moving away from each other where they're not supposed to be. Which, if we disable the parts resetting, is an actual problem that would happen. But it wouldn't be too efficient to reset every model at the start of every frame, especially the ones that never move. What the game does on startup is to search through all the models and objects with that flag, and then they're cloned and stored somewhere in replicated storage. From there, an object value is created which links to the clone under the folder defaults, and similarly, under the folder model locations contains links to the models that we want to update every frame. Also, to note is that every moving part has a unique name, otherwise indexing them would not work. And finally, we're ready to talk about the main part of the code, the animation script. This is the script that does all of the setting up and does all of the main animation loop. Here's a breakdown of what's inside of it. First thing we do is we wait for all the build scripts to finish setting up. This was the folder of scripts that I mentioned in my last explanation video, which takes the original model and builds up from there. One of the last scripts in this list being the copy original scripts, which is the one that finds the M flags and clones their default positions and all. Next, the MIDI is imported. This uses its own complete system, again its own video, but basically it creates a MIDI table. The import MIDI script is really important here. It takes all of the imported MIDI data and then creates note information based on what we want to play and stores them in anim table. It also has the code to initialize all of the keyframes, so it runs all the logic that we talked about in the previous video. That being the lookup matrices and then looking between the notes, that kind of stuff. Third, we keep track of all the prototype animation classes in the animations folder. And we call them prototypes because these will be the classes that we make copies of for every note we want. For example, the vibe note scripts gets stored as a prototype class. And then every time we want to make a vibe note object to represent one note in the song, specifically for the vibraphone, we copy the prototype by calling the new function. Fourth, we then use these prototypes alongside with the note data we stored in anim table to create all of the animation objects. In Pipe Dream, there's a 1-to-1 correspondence of notes being played and marbles fired out. So you can think of this code as handling all of the marble animations. Anyways, now that everything is set up, we need to define a draw function. This is the code that runs every frame to update the model and the camera. The loop is essentially as follows. Reset all the moving parts to their defaults, apply the keyframes, run through every AnimEvent and apply the ones we need to do, and then update the moving auto arc curves. In the main loop, which calls the draw function, there's some other code in there, but most importantly, there's code to update the entire scene and the camera's position. At this point in the video, there are two things I haven't really touched on yet. the animation events, and the camera movement. And in this game, I used object-oriented programming for a lot of the code. I used this tutorial which I found online for it, and I followed it. Eventually I got it working, so now I can create different classes, assign properties or functions to them, make them descend from other classes and all. Anyway, so now that I had that all figured out, I could use my Lua code like almost any other object-oriented programming language. So now I can think of my code visually as animation objects, and each one will be represented by an actual object and have all the right properties in the code. Visually, this is what the animation script is doing. The red line here is the current time t. Every animation event you can see has a start time and an end time, which is represented by the rectangle's left and right points. I call this the time domain, by the way. So we can see that if the current time is between an event's start and end, then we have to apply that specific animation. Furthermore, we can find out how far along that animation we are by subtracting the current time to the time the note needs to play. This number is then applied to the animation function that's inside the object, which we talked about last video. It then takes its effect and then adds it onto the correct model. So next, let's look into the base AnimEvent object itself. Remember that all animations with marbles are descendants of this class. So you can see every animation has a name, start and end time, model which it acts on, and pitch information. For every animation there's also a unique part, which means there's an object in the game that only appears for that specific note. Namely, this object is the marble. You can see under the original animation scripts that there's an object value which links to the master marble object. This is what's cloned onto each event whenever the animation is being set up. The import MIDI makes a copy and then assigns it to the correct event. I wasn't too sure where to keep the unique objects when they're loaded in, so I just made a folder called temp parts and I keep them in there. The only other unique part for an animation other than a marble is the pieces for the marimba animation. Each bar is unique to its own note or its own event, so those are stored under marimba as well. And I'll just run through all the other functions of the AnimEvent. We have functions to load and unload the unique parts, which keeps the game from having to render too many of them at once. There's also a whole system I even forgot about for rendering the auto art curves of a model. This code isn't part of the actual animation though, it's sort of the background code that handles the animation. Now we get into the final feature that I want to talk about, as well as the final one that I've added so far, the camera. I realized that what the camera does is completely separate from all of the other animations, which makes sense now that I think about it because it's the only animation not controlled by MIDI data. Really, as I started to work on the camera, I realized once more that it's nothing other than a parametric function with respect to time. We need to know the camera's position and rotation, stored as a Roblox keyframe, as well as its FOV value. And it turns out I'm using the exact same keyframe logic for the camera that I've used for the other parts of the animation, except I've created a different system for it so far. Just like how all of the animation code is stored in an animation folder, the camera code gets its own camera folder. Most of this, by the way, is a work in progress, so folders will change eventually. Anyway, you can see clearly that all the keyframes are stored inside this folder, keyframes. Storing their values out here instead of inside a script makes it possible to edit them manually, as well as making it easier to communicate with a camera plugin that I might have been working on for a couple weeks. More of that on its own video. The keyframe table is pretty much the same as the anim table from earlier, only for the keyframes. And for the position of the camera, there are two different modes to interpolate them. First is linear, and then splining. It's pretty straightforward to know what these are supposed to do. One's just a straight line and the other's all curvy. But to actually implement them, well, after some thought I came to a conclusion. For the spline, the starting and end points of the camera is nothing other than starting and ending C-frames. Solving the problem for where the camera goes over time is really the same problem as creating a smooth arc along two parts, meaning I can really just reuse my AutoArc code for this. AutoArc being my implementation of Bezier curves into Roblox, which I talked about in my previous explanation video. This video is almost over, by the way, don't worry. All this math takes place in the camera updater script, which is where the heart of the camera really is. Inside it, there's a few things we do. First, we use all of that AutoArc logic I talked about earlier. Each one of the splines has information associated with it, so we iterate through all the keyframes first and store what we'll use later in this table. Then, we're ready to define the camera function. This is the main parametric function I talked about earlier, by the way. The first half of all of it is just the keyframe code I talked about earlier. The variable alpha just means how far along the path from 0 to 1 we are. So if we're halfway between the 2 points, alpha is a half. If we're 75% of the way, alpha is 0.75, and so on. Now is where we get into the spline part of the code, the last thing I've added to this animation so far. First of all, if the keyframe is not a spline, we update its position linearly. This is the part where the math gets kinda messy, but the basic idea is the splines travel along the Bezier curves, and sometimes they speed up or slow down. In general, I wanted 2 splines connected to each other to look like one big spline, and I'm still working at it. But for now, that's the end of the video. I know it's been a while since the last one, and honestly, I'll work on and off on this project. For now though, thanks for watching. I hope some of this made sense to you. But yeah, long video. Glad it's finally out. Thanks for watching.